So first thing to note, as I've written here, is that there won't be a class on Tuesday. I understand that this Charles University has a holiday on Tuesday since it's right after Easter. So, well, you can try to come, but unfortunately, no one else will be here. Okay, so let's get started. So last time, we finished with a theorem about the vectors, the tensor product of two Hilbert spaces. So we had H and K Hilbert spaces. Then there exists a unique inner product on the vector space tensor product of H and K, satisfying if we have two simple tensors and we put them into our tensor product, then it's the same as just taking the tensor product of each of the tensor factors and multiplying together. And then the Hilbert space tensor product of two Hilbert spaces is going to be the completion of this algebraic vector space tensor product with respect to the induced norm from this inner product. And denote that with a little hat over the tensor product symbol. And then we also observed that for a simple tensor, the induced norm does exactly what we want it. So it's just going to be the multiplying the norms of the two tensor vectors. And that is an easy consequence of the definition here of the tensor product, of course. And I believe we stated but did not prove the following lemma. And that's about the tensor product of two bounded operators. So if we have an operator on H and a bounded operator on B, then we can take the tensor product which we define to be the unique operator, denoted A tensor B hat in the H tensor K hat, such that if we take the operator and apply it to one of these simple tensors, then we just get a tensor product of A applied to chi and B applied to eta. And moreover, the norm of this operator, A tensor hat B, is just the same as taking the norm of A as an operator on B of H times the norm of B as an operator in B of K. So first we'll define an operator on the uncompleted tensor product in the obvious way. So if we have some element in our vector space tensor product, then it's just going to be a finite sum of simple tensors. So for some n, we have something like this, and we'll define this to be and what we need to show is that well, that this is going to define a linear operator. That's pretty straightforward to show. So, and that it's well defined as a element of the tensor product. So I'll leave that as a little exercise, I suppose. And then the main thing is to show that it's bounded, so it will extend to a bounded linear operator on the completion of H tensor K. And then, of course, we denote that by a tensor B hat. And then this uniqueness statement will be clear because we defined it on simple tensors, and those generate H tensor K. So any other operator that satisfies this this here will be the same operator. So uniqueness will follow from just showing existence in this case. Okay. So first we observe that B of H and B of K are both unital. And we saw in one of the first lectures that any unital C-star algebra is spanned by its unitaries. So it's enough to assume that both A and B are unitary operators. Since if we can extend any unitary operator of this form, then we write our element as the sum of unitaries, and it will also be bounded and it will extend. Okay, so let's take an arbitrary element in the tensor product, zeta. This is sum of simple tensors. And then we observe that we can write each A to I as a linear combination of elements in orthonormal basis for the span of the chi i's, which will be very useful. So let's do that. So let me just say that, write that down. So we write each chi I as the span Oops. It's a linear combination. We don't really need the whole Hilbert space, but just the span of these. And we do that, and we can reshuffle things and maybe change the chi-i's. So we can assume that we have written zeta in a way that all the chi-i's are pairwise orthogonal. Now, since we're assuming A and B to be unitary, we can calculate the following. So take A tensor B, apply it to zeta. That by definition is just going to be the sum of A applied to chi I tensor B eta I. And since these beta i's are orthogonal, we get that this is exactly I equals 1 to n. Which is, of course, just by the fact that these are unitary. I guess we could have done the unitary thing in the step before, but anyway. Oops. That's just the norm of zeta squared. Okay, so this tells us that the norm of A tensor B is 1. So in particular, it's bounded. So we can extend it to an operator, which we will denote A tensor hat B. And this is evidently the operator satisfying this condition. And as I said at the beginning, uniqueness is then clear. So we just need to check the condition on the norm. So we'll define a map from BH to BH tensor K hat, which sends A to A tensor the identity on K. And then similarly, I can do the same thing for B tensor K. Both these maps we see are injective on H into H tensor K. And since this is dense, these maps are injective and clearly star homomorphisms. And any injective star homomorphism is automatically isometric. Okay, so this is then the same as taking which by properties of operators on a Hilbert space is bounded by, oops, or I guess even more generally, the fact that this is a C star norm, so it's going to be some multiplicative. And this is isometric, so that's just the norm of A times the norm of B. Okay, so we need to show the bound in the opposite direction. So assume that they're both non-zero. Otherwise, there's not much to show. We can find two unit vectors such that when we apply A to chi and then take the norm in the Hilbert space, then that is greater than the norm of A minus epsilon, which is of course greater than 0, and similarly to eta. And then we can use what we observed right at the beginning, which is that if we have two elements in our, well, if we have a simple tensor in our Hilbert space, then this is just taking the norm in the separate Hilbert spaces. And that is, of course, then by our choice of vectors, we get this. And since epsilon is arbitrary, we must have that I should have a hat there, I guess, that this is greater than or equal to a norm of A times norm of B, which is what we wanted to show. So indeed, the norm of A tensor B is just the norm of A times the norm of B. Okay, so just a quick observation. You can see that we can multiply in a nice way in B of H and B tensor HK. So we can check that if we have an A prime in B of H and B prime and B of K, then we can define their multiplying A tensor B hat to A prime tensor hat B prime in the obvious way gives us another bounded operator. And similarly, we can define an involution or an adjoint operator in the obvious way by just taking A hat tensor B hat, and this is of course going to be also in H tensor K, and this makes B of H tensor K into a star algebra. So it's easy to check that that's true. Now, more generally, if we just happen to have two star algebras to begin with, then just making some arguments about using the universal property of vector space tensor products. One can show that defining this multiplication in an analogous way that's in will denote the algebraic tensor product of star algebras with this circle dot, so it won't be confused with the eventual C-star algebra tensor products that we have. And similarly, we can define this star this makes this tensor product into a star algebra. And in fact, these are, in a sense, the unique multiplication and involution that do this that extend the multiplication and involution in A and B in a reasonably suitable sense. So there are other ways of defining an algebra on the tensor product. But for example, this will, if B happens to be unital, then we can always map A to A tensor 1B, and these will extend the operations in the obvious way. So I'll just write that these are unique in a suitable sense. So in particular, if we have two C-star algebras, A and B, we can now take their vector space tensor product and put a star algebra structure on it. This is not necessarily going to be a C-star algebra. And in fact, there are some subtleties there. You can't just immediately stick a norm on this and complete and hope that you get a C-star algebra. However, we do have ways of turning this into a C-star algebra, completing it to a C-star algebra. They just might not be unique. So let's start with the lemma. So if we have 3 star algebras, and star homomorphisms, A into C and B into C, and their images commute. So by that, of course, I just mean that phi A psi B is the same as psi B phi A for A and A and B and B. Then there exists a unique star homomorphism from the tensor product of A tensor B, which we will call pi, satisfying pi A tensor B is just 5A times psi of B. So again, if we show that this homomorphism exists, then uniqueness is automatic because we've defined it on these generators. Okay, so the first thing is to check that this is indeed well defined. That's not very difficult. So we take A1, A2 in A, and B lambda in C. We just need to check that this map preserves the relations in our tensor product. So that's pretty much immediate, but let's just do it this one time for this. For the A side, B will be obviously analogous. Okay, so this is a star homomorphism. So we get that this is phi A1 psi B. And that is, of course, just pi A1 tensor B plus lambda pi A2 tensor B. And similarly, if we do the same thing with respect to B, so we see that pi is well defined. I suppose one could also just say that we know that multiplication is bilinear. So that's essentially why this turns out to be well defined. That this is multiplicative is, well, let's do the star first. Why would we do this? Essentially just so that you see why we need that the images commute. Okay, so this is by the definition of our star on the tensor product, just pi of A star tensor B star. That's going to be, by definition of pi, phi of A star psi of B star. These are star homomorphisms, so we can move the star outside. And this is where we need that these things commute. So this is psi of B, phi of A star, which if these didn't commute would not give us pi A tensor B with the star on the outside, but it would give us something else. So we want that these commute, we get phi A, psi B, which gives us the result. So start preserving. Multiplication is similar. And again, it really relies on the fact that the images of these two maps commute. Okay, so this is useful because the embedding of one star algebra into the tensor product of it with another, the images of A and B will commute. If we embed A and B into their tensor products, then their images will commute. So we have the following observation. So if we take another star algebra, and we have maps now phi A to C and psi B to D. Oops. And this is just defined by phi tensor psi A tensor B. This gives us a well-defined and this is just essentially the observation that C and D themselves commute with each other. So if C is in C and D is in D, and we assume that C and D are unital, then we have that C tensor 1D and 1C tensor D is the same as 1C tensor D and C tensor 1D. And any star homomorphism, including in the sense of in the C-star algebra case, we can always just extend it to be unital. So this makes sense even in the non-unital case. Times it, okay, 12. Okay. All right, proposition. My now not making streaks, but it doesn't want to write, which is a bit annoying. Okay, let's try that again. Proposition. Take two C-star algebras. And representations of those C-star algebras. then what we want to do is find a representation of the tensor product. So we get a unique star homomorphism pi from this tensor product as star algebras into V of H tensor K, such that pi A tensor B is phi of A psi of B. And moreover, if both these maps are injective, then so is pi. Okay, so let's define a map phi prime from A into B of H hat tensor K. So I guess this is sort of the observation I just made. We can always define such a map by just taking phi of A in the first tensor vector and then putting the identity in the second. Similarly for psi prime. By sticking it in the second tensor vector. Then, as I observed here, their images will commute. That gives us a map on our algebraic tensor product. Which is the map we want. So by the previous lemma, this is phi prime A prime. Well, that's just phi A tensor ID K times ID H tensor psi A, oops, B actually. Which is just what we want. That should have the hat, sorry. Okay, so we need to show that if psi and phi are injective, so is pi. Oops. So let's suppose that there is some C in the kernel of pi. And we can write, this is the algebraic tensor product, so C as the finite linear combination or finite sums of simple tensors. And similarly to the trick we did before, rewriting things, if necessary, we can assume that the BIs are linearly independent. Well, in that case, since psi is injective, their images will also be linearly independent. And then we get that pi of c is 0. By definition, pi is just phi ai tensor psi bi. These are linearly independent, so we get that it must be the phi ai's that are 0. But phi is also injective. Which means that the AIs themselves were 0, which means that C is 0, and so pi is injective. So this is useful because now we see that if we happen to have C-star algebras, and these are star representations of C-star algebras. So I said C-star algebras here, but actually probably only needs to be star algebras for anything I said now. But in any case, if we have two injective, so faithful representations, which means that phi and psi are injective, then we can extend it to we can use this to define a norm on a tensor B by just taking the norm from this Hilbert space. So in particular, we can do this with respect to the universal representations. So recall that the universal representation was this one that we built from states, and it's always faithful. Oops, we don't want it to be H. We'll call it K. Then from the previous proposition, we get that there's an injective star homomorphism. And then for C in A tensor B, we can define the norm, which we call the minimal or spatial norm. So we decorate it with this little min at the bottom. This is defined to be the norm of pi of C in this as an operator in this Hilbert space. Since this is just one side is the operator norm, it's clear that this is going to be a C star norm. And this norm satisfies A tensor B. Min is a norm of A, norm of B. And we complete. And this gives us the minimal tensor product of two C-star algebras, which is, again, a C-star algebra. And this is also sometimes called the spatial tensor product, because we're stealing the norm from the Hilbert spaces. And we write that as a tensor with a min underneath. And it's just the completion with respect to this norm. And since this norm will satisfy, as I just mentioned, the C-star equality on this dense subspace, we see that indeed this is a C-star algebra. So what we've done here is take a star algebra and a star homomorphism into bounded operators on some Hilbert space. We use this to put a norm on the star algebra, and then we complete it. And this gives us a C-star algebra. And this is the kind of thing you'll see over and over again in C-star algebra theory. So especially in the later parts of this course, when Tristan, for example, talks about things like group C-star algebras and cross-product C-star algebras and group-weight C-star algebras, this is the kind of thing you do over and over. You define a suitable star algebra, and then you complete it with respect to the norm that you get from a suitable Hilbert space. Okay, so this isn't the only norm that turns that allows you to complete this star algebra into a C-star algebra. And I'll finish off. Let's see what time it is. 12:20. Yeah, I should have some time. I'm going to have to be a bit skimpy on the details here, unfortunately. Because I'd like to be able to define maximal tensor product. And the minimal tensor product and the maximal tensor product are sort of the ones you most often will come across in the literature. And they both have different reasons for why you might choose one or the other. So as I was mentioning, in general, this might admit more than one C star norm. Which means that we have potentially many different C star algebra tensor products of these two that are not necessarily going to be isomorphic. However, these norms will all have certain commonalities, which we will see here. So if gamma from the algebraic tensor product is a norm satisfying the C star equality, we can denote its completion by a tensor product with a little gamma at the bottom. With respect to the norm gamma. Okay, so we have about half an hour left. So I will probably skip the proofs of most of these things. You can find them in the notes in the book, or also in the Murphy's book deals with tensor products. I don't believe that these are covered in the Davidson book, but you can find them for sure in Murphy and probably elsewhere. So the first important thing to note is that if we have a C star norm and we have some fixed A prime and B prime, then we can always define maps into the tensor product here, oops, by mapping A to a tensor B prime, and similarly B gets mapped to A prime tensor B. These are always continuous for any C star norm. So this is somehow like the minimal thing you would expect out of a C star norm, the tensor product, and indeed this turns out to hold. So as I said, I will skip the proof there. So that we can move ahead a bit. And this is useful because it can be used to prove that the following. So if A and B are non-zero C-star algebras, so this is in a sense going in the other direction. So if we have a representation of the tensor product with respect to this tensor norm, some C-star norm, this is a non-degenerate representation, then we can always find non-degenerate representations of A and B that interact in a suitable way with this pi here. Which will denote pi h, pi a, and h pi b, respectively. Such that pi of a tensor b is pi a times pi b of b. So if we compare this to the similar things before, last time we had two representations of A and B, which were not necessarily on the same Hilbert space, and we were able to get a representation of the tensor product. Now, from the representation of the tensor product on some H, we can always find representations of A and B on that same Hilbert space. So you can see that representations of A, B, and their tensor product are all related, which is not such a surprise, but something one has to check nevertheless. Okay, so we need a little definition here. So we have a star algebra. And if we have a map of gamma from A to positive reals, this is called a C-star seminorm. If it is a seminorm, so recall that a seminorm is the same as a norm, except for we don't necessarily have positive definiteness. And we want this to be submultiplicative. We want it to preserve the star. And of course, we want it to satisfy the C-star equality. Oops. So it's essentially just a C-star norm that's not necessarily positive definite. Now recall that we observed that the minimal tensor product has this nice property here, that the tensor product of the two operators, its minimal norm is just the norm of the two elements. Sorry about that, just had to close the door there. And indeed, any C-star semi-norm on the algebraic tensor product will at least be bounded. The C-star semi-norm applied to a simple tensor will be bounded by the norms of A and the norms of B. And the proof of such a result, essentially, it goes through the fact that we could decompose representations in this way. And now we come to an important theorem, which I will not prove because it's actually quite, reasonably involved. It's a non-trivial result due to Takasaki. Which says that any C-star norm on the tensor product is bounded below by the minimal tensor product norm. And this is why it's usually called the minimal norm. So now we see why it's called the spatial norm and the minimal norm. I would say more often you hear it these days called the minimal tensor product. So as I said, that was a very important result at the time. And this led to the concept of nuclear C-star algebras, and Takasaki also showing that, say, commutative C-star algebras were nuclear. Nuclear means that all of these C-star norms on your tensor product coincide. So this is a nice, well-behaved class of C-star algebras that we'll probably talk about more in the future. But a nice also proposition or corollary that we can see immediately from this is that for any C-star norm, gamma, we have that gamma A tensor B is the norm of A times the norm of B. So this can be a little bit, confusing maybe, because we have all these different C-star norms and their C-star algebra completions are not necessarily the same. But they all have this dense subalgebra inside. So can be a bit confusing at first to get used to this sort of thing. Okay, but now we know that, for example, the C star norm of the minimal tensor product is always smaller than any other C star norm. So as a consequence, for example, unlike what we might have for algebraic tensor products, if our algebraic tensor product admits more than one C star norm, so by that I mean our completions are honestly different C star algebras, then A tensor B gamma will never be a simple C star algebra. Because essentially you'll always get a map from A tensor gamma B onto A tensor min B, and this will have a kernel. So you just get that map by extending the identity map from the dense subalgebra. However, one of the reasons why the minimal tensor product is often used or preferred in certain settings is again a result due to Takasaki, and non-trivial again, so I won't prove it, that the minimal tensor product of two simple C star algebras is again a simple C star algebra. So simplicity is preserved under minimal tensor products. Oops. And the minimal tensor product is again very useful for preservation of properties of your C star algebras. So this is one reason why one often works with the minimal tensor product rather than an arbitrary tensor product. Okay, so we have a minimal tensor product. Natural question is, should we have a maximal one? And indeed, we do. Oh, but first I wanted to say actually that, okay, so when we built the minimal tensor product, we used the universal representations. And one of the key things there is that they were faithful. And we knew that we can take this tensor product of faithful representations and get something again that's going to be faithful. Now, of course, any faithful representation of a C star algebra, its image will be isomorphic to the C star algebra itself. So one might ask if we really needed to use the universal representations of A and B, and indeed we didn't. So the minimal tensor product does not depend on the choice of faithful representation. So what I mean by that is if H pi of A is a faithful representation of A is a C-star algebra, of course. And not H, we don't necessarily have the same Hilbert space, of course. K pi B faithful representation of the C-star algebra B. Then the tensor product representation, take its operator norm in H tensor K. That's just the usual norm of B of H tensor K. This is going to be exactly a C star, C norm of C min, and that's for every C. Okay. So we can also always take the tensor product of maps with respect to the minimal tensor product. So A, B, C, D, these will be C-star algebras. So this is the minimal tensor product version of what we saw for algebraic tensor products. So we have 2-star homomorphisms. And there exists a unique star homomorphism, which we will denote by phi tensor psi from A tensor min B to C tensor min D, satisfying the obvious thing. And if these both happen to be injective, then so is the tensor product. Okay, so again, we saw that this is true for the algebraic version. So basically the idea here is just to show that if we consider the map of algebraic tensor products given by which we know exists, we just need to show that this is bounded with respect to the minimal tensor product. Sorry, the minimal norms on both A tensor B and C tensor D. That means it extends, and then it's not so difficult from there to show injectivity. Okay, so I believe I will finish with just some comments about the maximal tensor product. So let's put curly T to be gamma. Gamma is a C star norm on A tensor B. So AB here are C star algebras, of course. So this is the collection of all C star norms on our algebraic tensor product. And then for some zeta in the algebraic tensor product, we can define a norm by taking the sup of all of this. Should be a gamma. Gamma, not C, zeta, sorry. And then we define the maximal tensor product of A and B. To be the completion. And we put a little max under our tensor product. Okay, so why does this max even exist? Well, that's because we saw that for any sorry, again, go away, A and B. So indeed, this is bounded. Oops. And of course, since all of these gammas are assumed to be C star norms, it's also easy to see that this will then be a C star norm, so that A tensor B is a C star algebra. And this is obviously called the maximal C star algebra or the maximal tensor norm because it will be larger than any other C star norm on A tensor B. And what's nice about the maximal C star norm which is something we don't necessarily have for the minimal, is this universal property. So if we have A, B, and C are C-star algebras, phi A to C and psi B to C star homomorphisms with commuting images. Then we can always find a map from A tensor max B into C such that pi of A tensor B is phi A psi B. So I have about 7 minutes. Maybe we could prove this, and then if I have a few more seconds, I will just say a few words about. Okay, so we know that there exists a unique map on the algebraic tensor product into C because phi and psi have commuting images in C, and this satisfies phi tensor psi A tensor B is phi A psi B. And we'd use a fun little trick here. So we define gamma A tensor B to positive reals by sending zeta to phi tensor psi zeta and take the norm of that in C. Well, this is the C star seminorm. So it's again, almost a C star norm, except for it doesn't necessarily have positive definiteness, but we can fix that by taking the max of gamma and the minimal norm. This defines a C star norm. So the fact that we've taken the max with the min, and the min is in fact a C star norm, so this will enforce the positive definiteness condition, and we do indeed get a norm. And it's got to be bounded by the max norm. way of saying it. So it's bounded with respect to the max norm. So we can extend it and since it's the extension of phi tensor psi, we see that indeed it satisfies this here. And again, uniqueness is clear because it's defined on dense subalgebra, uniquely defined on a dense subalgebra. So maybe just a quick definition, which I mentioned before. We say that a C-star algebra A is nuclear, nuclear if for any C-star algebra B there exists a unique C-star norm on a tensor B. So what does that mean? That means, in particular, the min and the max norms always agree. And so since any other C-star norm is in between there, again, all of these C-star algebras are the same. I guess probably just up to isomorphism. And these are particularly nice because now we can use, for example, the universal property of the maximal tensor product, but we can also use the fact that the minimal tensor product has this has good preservation of properties. So these are a very well studied class of C-star algebras. And just one other quick comment with 1 minute left. This idea of having this max and min norms is not just something we see for the tensor products. So recall that I said one thing we often do is find a suitable star algebra and represent it on a Hilbert space. Where am I looking? And then complete with the norm that we stole from the Hilbert space. Well, just like we see here, there's often more than one norm. There's more than one way to do this. So there's more than one way to take whatever suitable star algebra we have and find a representation on some Hilbert space and then complete the star algebra. There's usually more than one way to do it, except for perhaps in these special cases of nuclear C-star algebras. So you will usually get a maximal and minimal version of all of these things. So what are some examples of nuclear C-star algebras? Yes, compact operators are nuclear. More easily, it's not too difficult to see that the n by n matrices are nuclear. And you can see this by taking the tensor product with any C-star algebra A, and you'll see that this is in fact already complete. And since we know that if you have a C-star algebra, then the C-star norm is unique. So that means that this, all tensor products have the same C-star norm. More generally, any C of X is nuclear. That's a result of Takasaki, which is not very easy. But it turns out that nuclear is equivalent to something called the completely positive approximation property, which perhaps Tristan will talk about. And this basically means that you can somehow, you have good finite dimensional approximations of your C-star algebra. And in this picture, it's actually not too difficult to show that C of X is indeed nuclear. So it's easy to show that C of X has the completely positive approximation property. It's difficult to show that C of X is nuclear, but these turn out to be the same. Of course, the fact that they're the same is, again, not an easy result. But yes, there are many examples of nuclear C-star algebras. Of course, if you take the tensor product of two nuclear C-star algebras, that will be, again, actually, it doesn't even need to be compact. It can be just locally compact. So I could have put. So I hope that answers your questions, Philin. It's just a locally compact tensor space. So I guess I could have rephrased this to say that any commutative C-star algebra is nuclear. All right, so reminder, no lecture next Tuesday. And I will be more or less signing off as well, and Tristan will be taking over. And we will also let you know about these sort of evaluation we have in mind with these final project type things. We'll send you an email maybe in the next little while about those. So see you in a couple weeks.